Okay, feature selection. We just went through a lecture where we talked about how to engineer a whole bunch of features, and you can engineer way more features than you can ever practically use. You can engineer like n grams, 2 grams, 4 grams, 9 grams, 32 grams. You could go on and on and on and on, basically create an infinite number of features. And we'll see for a lot of reasons that creating too many features can cause a lot of problems with the learning process. And one of the important things to do to create effective models is to balance, just a couple of things: the complexity of the problem you're trying to learn, the available data, the power of the model structure you're trying to learn, and the features that you've engineered. A few of the problems that you could run into if you have too many features is, obviously, it's going to slow down the modeling process. If you think of logistic regression, it's got to learn one weight per feature, and it's got to keep updating that weight with gradient descent until it converges. So adding more and more and more features makes it just an intrinsically harder optimization problem. Another thing is that most machine learning algorithms, maybe not anymore back in the day, but you basically want to load the entire training set into RAM because of the way learning algorithms are going to process it. If you're streaming the data from disk, you're going to be significantly slower. So you may want to control the number of features you have so that your training set fits into RAM so that you're able to learn much, much more quickly. And then the third one is what I talked about with that combination of amount of data, types of features, modeling process, in that these optimization problems can be hard, they can be tricky, and they can confuse the learning algorithm and have the learning algorithm end up with something that happens to look good by chance, but isn't actually representing the problem that you're trying to get it to learn. And we're going to have several lectures and explorations of this topic of overfitting and underfitting, or bias and variance of the models, the learning process that you have. So these are some reasons you might want to do feature selection. In general, feature selection algorithms work by estimating the quality of the features that you make available to them, and then using only the best features when building the model. So there's a couple of components you could see, and we're going to look at 3 different ways of estimating the quality of features in this lecture. But one thing to point out is that feature selection is like a learning process that goes before the machine learning algorithm, and it takes in a bunch of features, just a massive set of features, and essentially turns some off. You could think of it in a logistic regression. I mean, logistic regression could potentially do the exact same thing feature selection could do by setting a bunch of the weights to 0. And I briefly mentioned something like regularization when I was talking about the optimization and the loss back in one of the introductory lectures. Well, regularization is a form of feature selection. But in this lecture, we're going to talk about taking feature selection out of the learning algorithms, pushing it to a phase before the learning algorithms so that the data we present to the learning algorithms is just simpler, easier for the algorithms to work with. And the 3 that we're going to talk about in this lecture are frequency, selecting features by the mutual information they have with the Y values, the class labels, and accuracy wrapper, which is selecting features by how well the machine learning algorithm happens to be able to use them. So let's get started. And before we do it, let's talk a little bit more detail about the pattern for doing this feature engineering / feature selection that I just briefly went through, as it's like before the learning process. So here you have the raw data that is your training set. And so this is raw data, and I call it raw. In the case of the SMS spam problem, raw would be the actual text messages before any bag of words or tokenization or any of that sort of stuff. Then you go into this joint process of feature creation and model creation. And these things have to iterate back and forth, and you can see this arrow here going up and down between them, because feature creation is going to turn the raw text into something the modeling process can use, and the modeling process is going to do however well it does, and then you're going to probably want to update the feature creation process based on what you're seeing. And in some sense, the feature creation process becomes another set of hyperparameters to the modeling process. So in addition to step size and your convergence criteria, you're going to have and then here's the feature selection creation things that we're doing. And out of this process comes the model, like we talked about before, but now also out of this process comes some featurization parameters. And those parameters are essentially part of the model because they're going to be required when you see some new raw sample, some new raw text of an SMS message in practice. You're going to need to know, hey, what the heck did I do in the course of creating these features so that now I can go off and do that again. So this might be things like the words that were selected, like what is the vocabulary that you ended up with, but also, you know, if I see the word the, is that X4? Is that X7? Is that X9? So you need to keep these kinds of mappings somewhere, and you know, you can think of that as a featureization parameter. If you did things like TF-IDF, you need to carry the weights that you learned, the IDF, the inverse document frequency weights of how important the term was to the corpus that you use to select the features, to select those words. And then when we talked about normalizing numeric variables, you're going to need to bring along the mean and the standard deviation that you saw in the training set so that you can apply that to numeric parameters that you bump into at performance time. Then here we are, and I call it runtime X raw. So somebody just sent an SMS spam message. Boom, it's in a memory buffer. You need to put your machine learning algorithm on it and see what you get. So you take this feature parameters and you put them into a code that I'm calling featureize. Now this featureize code had better match the code that you have over there, like exactly. There's some pretty crummy bugs that you're going to bump into. If like over here you take the word the and call it X7, and over here you have an off by 1 error and you call the word the X6, that's a very hard bug to find. And the reason it's so hard to find is that it will affect the accuracy of the model in runtime, but it won't necessarily crash things. And so maybe your accuracy is like 0.5% worse at runtime than you expected it to be. It's really hard to bump into and figure out what's going on. So it's important, you know, and I'm probably going to say that same story or versions of that story again and again because, you know, in my career when I bumped into like things where I was just like, ugh, what do I do now? I mean, it was several times it was this. Anyway, so you run that code and then you produce the feature vectors. So this is the actual array, the big X, or, you know, X1, X2, X3, X4, whatever, and you're able to pass that to the model runtime along with this model, which I don't think I animated on the slide. So that's what we're going to try to do. Now let's talk about those feature selection algorithms, and I'm going to tell you the algorithm. In fact, I basically wrote the whole algorithm right there, and it's really, really, really simple. Just kind of to think about, like, well, should I do this? Why should I do this? Does this make sense? And the first feature selection algorithm is you just simply take the top n most common features in the training set. Go through a little example of what that means and sort of to illustrate the process, but here's the code from the framework that I provided. And just to show you, you create, so this is a class that I've provided, and you're going to have to fill out this function with a little bit more detail, but it produces an object called featureizer. Then you call create vocabulary and pass it the training data, the X and the Ys. Some of these feature selection algorithms will use the Ys. We'll get to that in a second. And you pass it the N for the number of words that you want it to capture. Now, at this point, featureizer contains all the information necessary to take in a list of XTrain raws or X raws and produce the vectors that you're going to need for the modeling, you know, assuming that this is the parameters that you want to use. These are the hyperparameters for your feature selection / engineering. And then you can just apply this, the featureize method, to the various data sets. So, you know, just to belabor the point, you create the vocabulary just on the training data, and then you apply it to all the sets that you're going to want to use in that modeling process. And then if you were going to deploy featureizer, this is the type of thing where you could serialize this object, and that could be, you know, that serialized version of that object could be what you deploy along with the model, the serialized model. Okay, so, you know, now let's look inside this create vocabulary function with this, and just, you know, it's very simple, but it's sometimes I think it just helps to walk stuff through. You kind of like gives time for your brain to bake in all these terms kind of in the context of us trying to do something. So let's say you took a set of messages and you ran bag of words, and here are the tokens that you have after that bag of words completes. Now, in addition to just saying bag of words, you can also count how many messages each of these tokens occurs in. So you could see that the word the occurred in 1007 of the messages in your data set. So now you have to do, the most complicated thing in this algorithm, and that is sort. I don't know if you saw these things sorted. It like fade in, fade out. And now you can just see what the top few are. In this case, you want 4, so you take the top 4, and these become the features, and all of these are essentially discarded, and you can remove them from the X vector, save the memory, no problem, la-di-da. And then in the featureizer object, you can represent it as a bunch of things. You could represent it as a list saying token ID is at feature ID 1. So you'd say 2, 1, or you could just, list them in order, because you could just have it like 2, U, blah, blah, blah. I mean, you can figure out how to represent stuff. The reason I'm talking about this is that you may have features that didn't directly come out of the bag of words. For example, you may have tacked on a bunch of handcrafted heuristic features like the length of the message or blah, 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 blah. And in that case, you would need to say specifically, when you bump into this handcrafted feature, which was at index, it looks like 77, you will output that feature as index 3 or whatever it is in the order. So, just to keep in mind, there's this duality where if all of your feature selection is plucking words, it's pretty easy to just ship a list of the words to use in the right order. But a lot of times you're going to have to mix and do a hybrid between them. So you may get a little bit more complicated than you would first imagine. But that is feature selection by frequency. Very, very simple algorithm. And it kind of goes on the assumption that tokens that occur more often are more likely to affect the modeling process. We saw with TF-IDF that's not always the case. Tokens that occur way too much don't tend to help. A token that's on every single message is basically completely useless. It functions as another bias weight. So you'd have like 2 biases and then partially cancel each other out, and the learning algorithm would put part of the bias it wants to put on one and part of the bias. Anyway. So we can do better than just saying, hey, things that occur more are, more. But it makes sense that a token that occurs on 0.0001% of your messages is unlikely to give you a gigantic accuracy boost. So you got to kind of balance between. Okay, but another thing you could do is actually look at how important a particular feature is to the value of y, and take the n features that contain the most information about the value of y in the training set. Everything you select based on what you see in the training set. And just a little, I get this question. It's a little bit like looking at the correlation between each feature and y, except for a slightly technical thing where correlation is the strength of a linear relationship between variables, and mutual information, which is what I'm going to draw right here, mutual information in a second. But mutual information is how much you learn about one variable by knowing the value of the other variable. You could take whole courses on all the different types of relationships between information and information understanding and processing and blah, blah, blah. But we're just going to keep it very simple and just draw this out because it's a common point of thought for people who come into seeing mutual information for the first time. And there's the definition of mutual information. And it says the mutual information between a variable x and a variable y is that you sum over all possible values that they take. So in this case, everything's binary. You can get more complicated, but let's just binary. And then you take the probability of that combination occurring. So since you're summing over these, you'd say the probability of y equals 1 while x equals 0. And that's that. And then you do this calculation of a log, which is the log of the probability of them occurring times divided by the probability of each independently. And that, if you think about it, this is the joint occurrence, and these are the independent occurrences. So it somehow relates all of those elements and how they work together. And that's what spits out a score that lets you know how much you can learn about y when you know x, and I guess vice versa. So the steps of doing this algorithm, let me just clean up my board here a second. The steps of doing this, it's very convenient. You can do it from a contingency table, which is a little bit like that false positive, false negative thing. And you'd say, you'd go over all the training data and you'd convert it into this table of y occurrences and x occurrences. And that's what you need to be able to calculate all of these statistics over here that go into this mutual information formula. One thing to point out at this point is that sometimes these will be 0. And if you plug a 0 into parts of this, you're going to get kaboom jobs. So you don't want to do that. And what we do instead is this little trick called additive smoothing, or you take you have a prior, a small prior, and there's going to be much discussion of what a prior is, but basically it's to say that you as a person, you know, like 0 is a very unlikely probability. So let's fill in some other value, and I'll bring my personal knowledge to the table and combine it with the statistical knowledge I see in the data set. And so that's called, I would have a prior. Anyway, there's lots of ways to justify doing this, which we'll talk about in more detail in later lectures. But for now, it just comes to the point of, you know, you add, when you're calculating each of these values, or the probabilities off of each of these values, you add a 1 to the numerator and you add a 2 to the denominator. And that just keeps you from busting out with division by zeros. And it's actually there's actually a good reason you might want to do that, even if it weren't for that little computational issue that you might bump into. We'll talk about it. So just working through the example, you would first calculate all of this. You got to do the summation, and you would calculate it for this square there. So the probability of that occurring jointly is 3 divided by whatever, 30%. This stuff turns into that. And so the score for 0, 0 is right. Then you're going to add the next cell, all possible combinations, and then you sum them all up. And it turns out that the mutual information in this case, according to this training data, is 0.086. Okay, what does that mean? Let's get a little bit more intuition about what the boundaries are here. And imagine you had a contingency table like this, which would say, you know, so if I know X, this is a question for you. If I know X, what do I learn about Y? Do I learn anything about Y for knowing the value of X? If I know X is 0, Jeopardy music time, blah, blah, blah. Think about it for a second. Okay, but yeah, I mean, it turns out that if you know X, you know Y. They're essentially the same variable. So in this case, you'd say it's a perfect predictor. Feature X is a perfect predictor of what you're trying to do among the training samples. And so it would have a very high mutual information score. Here's another sample we look at. So Jeopardy time, da 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 da. If you know X, what do you learn about Y? Yeah, and it turns out you learn zippo bizarro, nothing. You learn nothing. If you have X, Y just looks like, I don't know, could be either. In this case, there's no information about Y contained in X, and so the mutual information you get is 0. So you'd see, you know, like this feature selection algorithm would look at each X in the data set, perform this calculation for it, sort, and features that have this property where you learn nothing would tend to sort to the bottom, and it would be unlikely to get selected in your top N, whereas features that have this property would get selected very high. Although if you do have a feature that looks like this in your training data, what you probably have is not a good feature. What you probably have is a bug, or you're not thinking through something correctly, because you know, maybe you accidentally put your label in as one of your features, or maybe you've created a feature based on really spending too much time looking at the training data, and there's a feature that just works on training, the training data you happen to have, and is unlikely to generalize. So, you know, maybe you could just write a little exception, a little trigger for yourself that if you ever see a perfect feature, take a look at it, think again, make sure it's what you wanted it to do. So that's the second feature selection algorithm. And again, you know, they're pretty simple. It's just like, what's the evaluation you're using, and then sort according to it and take the top N. Now, N becomes a hyperparameter, and we'll see that it gets a little more complicated because you're going to have to tune that. But let's go on and talk about the third algorithm before we get to that, and that is feature selection by using accuracy, or sometimes it's called a wrapper method, because you wrap feature selection around a modeling process and use the modeling process to evaluate how good each feature is. And at the end of it, you take the N that improve accuracy the most on holdout data. Holdout data, you might perform all of feature selection on the training set, But, in everything that we talk about down here, you do your own additional holdout where you say 80% is used for the modeling and 20% is used to measure the accuracy. So this is not accuracy on the validation set or the test set. This is among the data that you're using to do feature selection. You got to create an additional holdout and use that when you're selecting features. Okay, so here you go. You could imagine a lot of ways to do this. Let's talk about a simple one, and that is a greedy search, either adding or removing features from a baseline. The baseline could be we start with every feature and we just remove them until we can't remove any more because we start hurting accuracy too much. Or it could be we start from using like no features and we add features one at a time. And I'll give a little example of that and some of the reasons that this type of wrapper method could be superior to the other two feature selection processes that we talked about just recently. So anyway, from a baseline, you try adding or removing each candidate. You build a model on that 80% of the data, and then you evaluate it on that 20% holdout that I just remember I drew it up there and then I erased it. So that, I don't know why I erased it. I don't know. Then after you've done that evaluation, you just add or remove the best feature according to what you're doing, and you repeat until you get to the number of features that you want to have. Now, this process optimizes not just for the labels, not just for the fact that the feature occurs a lot in your training data, but it also optimizes for the modeling process, which is what is my model able to take advantage of, and also, as we'll see, kind of the mutual information between the x's, x1 and x2. And here, let me just walk through a little example of what that might look like. So let's say you're trying to pick 2 features or 4 features or whatever, and here are the tokens that we've seen on previous slides, and then here's the mutual information calculation that we've done for each of those features. So this is how much do you learn about Y by knowing that the token 2 is or is not in the message. And, 0.3, 0.2, blah, blah, blah. And you can see right here, there's sort of 4 pretty good features. And then there's a set of features that are kind of like, they're okay. I mean, it's not zeros, but if you were going to take the top 2, top 4, you would prefer to use these, at least according to mutual information. And then there's probably some features that are pretty junky, like, right, okay. Anyway, so there you go, thinking about what mutual information would do. Now let's go and build a model. So step 1 is that we do this 80-20, holdout, blah, blah. You can run the exact same model you're trying to learn. If you're trying to learn a logistic regression, you could do a logistic regression here and do a little bit of hyperparameter tuning and make sure that these are based on at least partially tuned models. But remember that what we're trying to do now is just select features, not produce the best production model possible. So you might actually do things to save time, because this process could take a really long time. So you might do this accuracy estimation off of like a really simple model, like if let's say you're using neural networks because we're in the future and you want to blah blah something like that, you might come back and use a logistic regression to estimate this value. Or you might actually only use 10% of the training data that you have available, something along those lines. Or you might set a convergence that means that it doesn't run very long. Anyway, la-di-da. But you could see here that, again, these first 4 features that had high mutual information also have high accuracy. So now you're saying, well, why are we, let's just take the 4 and go. Come on, these are the best. They're producing the most accuracy. Mutual information confirmed it. This confirmed it. Take them and go. I guess we're trying to learn 2. But now let's do one more step and see what might happen. So in this case, you would pick 2, and 2 would be the first feature. So now you'd build another model that has 2 and each of these. You try adding one of each of these. So 2 and in, 2 and few, 2 and... And then here is what you get. Well, and you might see that, hey, this model had 77.2. Adding this next feature, it goes up 77.4. That looks great. But then what the heck's going on? This feature down here has an 80.2% accuracy. So this feature is the best feature to take for the second step, and well better than, taking one of these that were looking so good according to mutual information. And so what happened? There's a lot of things that could have happened, but one is that these 4 first features all have strong mutual information with the label that you're trying to learn, but they may have the same mutual information. They could be slight variations of the same kind of insight, the same portion of the concept, Whereas this feature down here might be a fresh look at what is the concept. It might expose something that none of the other features had exposed, and that second fresh look may not be as powerful as what these first four represent. But if you want to take two things, you want to get one look at it from the left and one look at it from the right, or whatever that other approach is. And in this sense, the wrapper feature selection has the opportunity to be a lot more accurate, because not only does it use like, hey, here are things that occur a lot and thus could have a large effect, and they have something to do with the target label, but also they work well with the type of model I'm learning, and they work well with the features that I've already selected in. Okay, so now let's revisit our model evaluation creation process that we went through in, I guess it was lecture 3 or 2 or 7, or I don't remember what, probably 2. And here is what we saw before. And I'll just walk through this again. You've probably gotten to this in homework assignments already, and then we're going to do a slightly more complicated version of this that includes feature engineering and feature selection. Here is the pattern that we looked at before, and would say for each hyperparameter to try, which might be step size, convergence, etc., build a model on the training data using that parameter, evaluate it on the validation data by having the model predict it and comparing it to the true validation labels, store that in some accuracies lookup table from the hyperparameters to the accuracy. Then we find the best set of hyperparameters using this, Python wizardry, and we build a final model on, bring as much data to bear as we can, the best hyperparameters. Then we estimate generalization performance on the test data, look at, is that good enough to ship? Great. Now we want to add feature selection to that. So you've seen that, so we have to do this for F in feature creation parameters to try. And this just adds another layer of loops. And this is one of the problems you start to bump into with machine learning, is that everything you do to get more refined, to be more accurate, to add more information, results in, maybe not a loop, but, more complexity in this modeling process, more models to try, more time to sit around waiting, more ways to torture whatever small amount of data that you have. And you might start off thinking like, hey, I got 3,000 samples. That's a gigantic amount of data, but you end up torturing it a lot. And so it's going to confess to all sorts of kind of weird things that aren't true. And this is why we'll see in future lectures why knowing a little bit of statistics will help a lot with this process that we're talking about here. So anyway, we have a whole bunch of feature selection parameters to try, which might be, use bag of words, use 2 grams, use bag of words and 2 grams, select N features using mutual information, select 2N features using mutual information, all the different things that you want to try. For each of those, you create a new SPAM featureizer object, and you create a vocabulary using whatever those parameters happen to be. Then you take that learned vocabulary and you apply it to the raw training and validation data. And then you hop into the inner loop, which is for the modeling hyperparameters that you want to try, you do that loop. And now in the accuracies, you store both the modeling hyperparameters and the feature creation hyperparameters that you used. Take the best among all of those, create the best featureizer. I mean, this looks very similar to what it looked like on the previous slide. And then you go off into all the evaluation stuff on the test set to make sure that we're generalizing well, et cetera, et cetera, et cetera. And like, I said, this is like, now we have 2 sort of brute force loops, but in practice, you're going to break this out and be a little bit more sophisticated and try interesting combinations that you think are likely to work. But that's a topic for a future lecture. So in summary, feature selection is a good thing to do, because using too many features can cause problems. It can lead to adding a bunch of irrelevant features, which might lead your machine learning to learn some gibberish, aka overfit. You might not have enough data to work with a gigantic number of features, and those first 2 bullets are somewhat related. You'll often want to do feature selection to save time in those gigantic nested loops that I just talked about. You might find often in practice that there's a lot more things you'd like to do that you just don't have your own personal time to do, and you have to make some decisions to allow you to do a proper evaluation and get finished, rather than build like the universally best thing. I mean, there isn't really going to be no universally best thing. And As we've seen, once you've built a model for today, you're going to immediately start building on the model for tomorrow. So there's some advantage to training efficiency. Then there's also the runtime implications of every feature that you want to use. Somehow you have to construct at runtime, build a vector, and then have the model that you deploy at runtime process all those features. And you might be able to save, critical milliseconds. It sounds crazy, milliseconds, but I've been on applications where we had like 8 milliseconds to do whatever we need to do in the budget. So feature selection algorithms will help you avoid those problems by finding reasonably better features than just randomly picking, using a kind of series of complexity, starting from frequency, which is a very fast thing to do, but has some disadvantages because things that are too frequent might not be particularly relevant, and it doesn't take any advantage of the labels that you have available or the Ys. It's just totally blind. It's an X only. It's kind of like an unsupervised method. You could use a slightly supervised method. It's a supervised method, which is mutual information. I just said slightly because it looks at the mutual information between each feature and the class label independently and kind of makes an assumption that they're not correlated. And we saw how sometimes they could be correlated. And in that case, you might want to use something more complicated like the accuracy wrapper method, which allows you to really pick the set of features that work best with your modeling process if you have a heck of a lot of time to do it and press the button and let it run. It would not be surprising, even using, in our assignments, that if you were going to do a really good version of the accuracy wrapper for a small problem that we're working with, you might be waiting overnight. Probably because, you're not using highly optimized versions of the algorithms, but you can spend a lot of time. And then in practice, everything is these pure algorithms never exactly get used this way, and you'll often do some sort of hybrid. Like you might say, hey, I have 10 million features I could consider, and I'm going to use frequency to, throw away half of them, something along those lines. Then I'm going to use mutual information to get me down to like the 1,000 that seem to be pretty decent, and then among those 1,000, I'm going to pick 50 using this method, or something along those lines. Sometimes it's really important to do these sort of sophisticated feature selections. Sometimes it's good enough to just say, hey, mutual information, I'll use triple the number of features I think are valuable, and I've moved it down from like 1 million to 1,000, and the machine learning algorithm itself can take it from there. It can set weights to 0. It can do what it needs to do. So feature selection doesn't need to be perfect. It's just trying to help you avoid problems before you bump into them a little bit down the road. So there you go. We've got another useful technique in our toolkit. Really starting to stack them up, and hopefully you're having fun playing with some of these in the assignments, and I'll see you next time. Thanks.